This diagram shows the structural dependencies of a standard topology course. Chapter 9 introduces the fundamental group, but to calculate it for complex spaces, you must jump down to Chapter 11. Calculating the fundamental group of a complex space directly from the definition of continuous loops is incredibly difficult. The goal is straightforward. If a complex space can be broken down into simpler, well-understood pieces, like basic disks or circles, we need a rigorous mathematical rule to add their fundamental groups back together. Instead of analyzing an abstract space X all at once, we decompose it. We separate X into two distinct subsets, U and V, making sure there is an overlapping region between them. The Seifert-Van Kampen theorem provides the precise formula for this decomposition. It allows us to combine the topology of these individual pieces into the fundamental group of the entire space. The theorem requires a strict setup. U and V must be open sets, and their union must equal the entire space X. We also establish a base point, x0, located squarely inside the overlapping region. Here is the requirement that catches most students. U, V, and their intersection must all be path-connected. A disconnected overlap would strand the base point, making it impossible to smoothly translate continuous loops between the two halves. When those conditions hold, the theorem states that the fundamental group of X is the free product of the groups of U and V, modulo a specific normal subgroup. The mechanical proof relies on the Lebesgue number lemma. Any wild loop traversing the entire space X can be chopped into tiny segments, such that every individual segment exists entirely within either U or V. Because the overlap is path-connected, we can pull the endpoints of these chopped segments back to our base point. This action translates the topological bluing of spatial paths directly into the algebraic operation of a free product with amalgamation. Let's calculate this for a wedge of two circles, commonly called the figure-8 space. You cannot split this into two closed circles. The theorem strictly requires open sets. We fulfill this by thickening the pieces. Extend the left circle slightly past the center point to form U, and extend the right circle slightly past the center to form V. The fundamental group of each thickened circle is Z. Their intersection is the small X shape at the center. Because that shape can be continuously shrunk to a single point, it is contractible. Its fundamental group is trivial. A trivial intersection provides no new relations to mod out. The fundamental group of the figure-8 is simply the free product of the two individual Z groups. Now we scale up to the two-sphere. Let U be the northern hemisphere extending slightly south, and V be the southern hemisphere extending slightly north. Pause here. Determine the fundamental groups of U, V, and their intersection. Then calculate the fundamental group of the entire sphere. Defining the overlapping region correctly is the point of failure for most calculations. If the overlap is misidentified, the algebraic quotient will be wrong. The open hemispheres U and V are topologically equivalent to flat open disks. They are completely contractible, meaning their individual fundamental groups are trivial. Their intersection forms a cylinder, which shares the topology of a circle. However, because we nap that intersection group into the trivial groups of the hemispheres, no new information is preserved. The fundamental group of the entire sphere is trivial. This gives us a highly reproducible method. Step 1. Pick open covers U and V. Step 2. Verify the covers and their intersection are path-connected. Step 3. Compute the fundamental groups of the pieces. Step 4. Apply the algebraic quotient. The Seifert-Van Kampen theorem takes spatial structures that are difficult to visualize and translates them into the rules of algebra, making exact topological calculation possible. If this visual breakdown helped you process the theorem, subscribe for more step-by-step guides decoding standard mathematical proofs.